This continues our discussion of building a power supply, and to review, what our goal is to bring 120 volts in, and this is volts AC, and we're going to produce about 20 volts DC. And I have to say about 20 because in this discussion we're going to be producing about 2.1 volts DC. And you can say that sounds awfully small, but it turns out it's something that many like modern electronics will use somewhere between 2 and 3 volts. So anyhow, we're going to continue doing it. Now, what's the problem with our unregulated power supply, the one that had the transformer, the bridge rectifier, and the capacitors? Well, first of all, we noticed that if we change the input voltage, instead of 120 volts, we put, let's say, 115 volts or 150 volts, is that we change that input voltage, the output voltage changes proportionally. So we do not have a stable value for the output voltage. Another kind of problem we have with it is ripple. We notice that the ripple is that kind of rippling effect that we have on the power supply. It looks like this as the capacitor charges and discharges, and we can make the ripple smaller by putting a bigger capacitor in or through the use of the full wave rectifier, but we cannot reduce the ripple to zero. And so what we're going to do is we're going to add a second stage to this, and we're going to add a regulator. And what this regulator is going to do, it's going to stabilize the output voltage, and it's going to reduce the ripple significantly. So this is this piece over here, this area is what we built previously. And so we now have ourselves about a 20 volt raw voltage, and then what we're going to do is we're going to add this piece, the regulator, before we actually present the potential to the output circuit. So this is what we've had before. It's in this square. You should have built it and you should have characterized it. What we're going to do is we're going to add this stage to it. This stage consists of a resistor, and then 3 diodes, and this is the regulator part, 3 forward bias diodes. Why do I say they're forward bias? Because this side is positive with respect to ground. And so those diodes in normal condition will be conducting current. And then we have, of course, our output resistor. This would be the load we're presenting the potential to, and of course we have an output voltage across it. So we have a current through it, and then we have a potential across it. And so the 3 forward bias diodes, okay, produce a 2.1 volt output voltage. Why? Because each of these forward bias diodes has a 0.7 of a volt drop across it, okay, as indicated by this diode graph. So what we find is that we're operating somewhere, let's say, at this point, which says that we have a forward bias of about 7 volts, and we have a current running through them. Okay. Now you say, well, what happens if we increase the current a little bit? Well, we increase the current a little bit. Okay, so for example, we increase the current, let's say, from this point to this point, is that what happens, that's a significant increase in the current or change in the current, but because of the slope of this voltage current curve, is that we have a relatively modest change in the voltage across it. So this gives us a fairly stable voltage as a function of current. And so this is the way we're going to try to get rid of all of these things. So we go on to next. And what we're going to do is let's ignore all of the transformer and the bridge rectifier and the capacitors, and we'll just concentrate on the regulator phase because this is the thing that we're interested in. Okay, so what we're going to find pretty quickly, it's useful for only very small output currents, and we'll find out why. And the issue is that how to pick this RD. So the question is, what is the value of that resistor? Now we have a Goldilocks problem. If we make the resistor too big, we won't be able to get current out through the resistor, because what happens is where's the output current come from? It comes from RD. Okay, if we make the resistor too small, we'll end up dissipating putting way too much current through the diodes. So we have to come up with the right value. And this becomes especially problematic when the output load can go between some zero current all the way up to some maximum current. Okay, it's the variability of the output that gives us the trouble. Okay, the output current. So, for example, if we happen to not have a load across here, so RL is equal to infinity, then we pull zero current through here. So where does all the current go? It goes down through the diodes. If we happen to have a very small RL, which resistor load, which means that we're pulling a significant amount of output current, then we want to make sure that this diode or the resistor RD does not drop so much voltage that we no longer regulate the diodes. So let's take a look at some of these, and we'll see if we can quantify that. The first thing is the potential across this resistor. Since this is V out and this is V raw, that potential always has to be this. Okay. If the current through this resistor RD is equal to the sum of the currents through the diodes and the current through the load. Okay, well, the diode current is generally relatively small. It's in milliamps to keep these diodes running, and the load resistance can change quite a bit. Okay, now since the output current can vary, okay, between 0 and some maximum value, this is the load current. Okay, and we have trouble finding RD. So I just went through that. We did it again. Okay, so let's look at an example. Typical example is the raw voltage, let's say, is about 12 volts. Okay, so that's there. The diodes require at least 2 milliamps, so let's put 2 milliamps here. That's going through these diodes. If the diodes dissipate less than 2 milliamps going through them, they no longer do this conduction trick, and so this voltage will drop across the diodes. The potential drops across the diodes. So we need to keep the diodes operating well on this curve. So this is that curve we did before. So we want the diodes to be operating here rather than operating down there. Okay, and then let's say the output current in our example, going back to that, ranges from 0 to 1 amp, which is actually 1 amp is fairly small power supply. Okay, assuming this, then we find the following: that the maximum value that we can have for the diode resistor RD is equal to the drop across the resistor. This is V over I. In this case, it's about 10 ohms. Okay, so if we have a resistor there, so if this thing is greater than 10 ohms, then what's going to happen is that as this current gets larger, then the dissipation or the voltage drop across this resistor becomes too large, and then the diodes no longer have enough current to support the regulation, and therefore this voltage will drop. Okay, so we can't have anything that's bigger than 10 ohms. Okay, so let's take a look at the power dissipated. If we have 1 amp output current, and then we have about 11 volts across that resistor, then that resistor is going to dissipate 10 watts, which is pretty toasty. Okay, now if RD is larger than this, then we already talked about that the diodes will no longer be able to regulate. Okay, and then our output current, our output voltage will drop. Okay, now what happens when the load is 0? When the load is 0, all the current goes through the diodes. Okay, you still need 1 amp or 1 amp plus 2 milliamps flowing through the resistor, and so this thing is going to dissipate about 2 watts. Okay, so the diodes need to dissipate 2 watts in here when there's no load. Okay, and so what happens is when we're doing this, the problem is power. Okay, so to review, is the power that's going through this is that we always have 10 watts being dissipated the load, we only get 0 to 2 watts across it. And the diodes, when we have full load, only have 4 milliwatts. But when we have no load current, then the diodes must dissipate 2 watts. So it's just the diode, this circuit works, but it's inefficient when we have large loads. Okay, now here's the other problem, is that we can end up with a tall stack of diodes because very few people want 2 volts. So if we wanted, let's say, 12 volts, which would be a typical output voltage, well, let's say it would take 12 volts, we have to divide it by 0.7 per diode, and it would take a stack of 17 diodes to produce this. And that's kind of silly. And the problem is that going down here, we're working in this area, okay, on the diode. Suppose we take another approach and reverse bias the diode, and you say, well, when we reverse bias the diode, we pull no current. That's true until the voltage becomes large enough. And then we have this thing that's called the breakdown voltage on the diode. And there's certain diodes that you can buy, and they're called Zener diodes. And Zener diodes have a very controlled breakdown voltage, mean that you know pretty much where that breakdown voltage is. It's precise, and also repeatable, and also it's very steep. And we need the steepness in order to regulate. So a Zener diode looks something like this. Okay, it looks like a diode, but it has little wings attached to the bar on the diode, and you plug the Zener diode in the opposite direction from the regular diode because we want the Zener diode to be reverse bias. In this case, this circuit down here works exactly as this circuit. Okay. Now the good news is I can buy Zener diodes that have breakdown voltage from few volts all the way up to hundreds of volts. So I can do this with one diode here. Okay, finally diode packaging. Diodes, we have axial packages, which means they look like a resistor, and that there's a stripe generally on the package, and the stripe indicates this side of the diode, okay, which is called the cathode of the diode, okay, and then the anode is in the back side. So if you want to have diode facing this direction, you just put the diode package in here. If you want, and the stripe will always give you that sign. And with that, I think we're done. You're about ready to go through and add a regulator to your power supply.